Hello everyone. Today we're going to explain two Python programs based on chapter 7, Let's Make Some Noise, where we work with image noising, filtering, kernels, and convolution using OpenCV, NumPy, and SciPy.
First, I will explain code 1, and the purpose of this program is to simulate two common types of noise in images, and then reduce that noise using low-pass filters. I start by importing OpenCV and NumPy, and then I load an image and convert it to grayscale. This is important because the chapter explains filtering and noise more clearly in grayscale, where each pixel is only one intensity value from 0 to 255. The first noise type I generate is salt and pepper noise. This noise appears as random black and white pixels, and in the code I loop through the image and generate a random number for each pixel. Based on a probability value p, some pixels become 0 and some become 255 and the rest stay unchanged. This creates the impulse noise pattern that we expect. Then I generate Gaussian noise, and here I convert the grayscale image to float, and I add random values sampled from a normal distribution using np.random.normal. And after adding this noise, I clip the values back to the 0 to 255 range and convert to unit Wint 8. Gaussian noise looks different because it changes intensities smoothly and produces a grain-like effect instead of impulse. After generating both noisy images, I apply the noising filters. For salt and pepper noise, I use CV2.medium blur. The medium filter is effective because it removes isolate impulse pixels while keeping edge better than a simple averaging filter. For Gaussian noise, I use CV2.Gaussian blur. This is a low-pass filter that reduces high-frequency variation, which is exactly the behavior of Gaussian noise. Finally, I display the original grayscale image, both noisy images and both filtered results, so we can visually compare how each filter works depending of the noise type.
Now I'll move to code 2. The goal of this program is to show how kernels are used in filtering and how convolution can be applied using both SciPy and OpenCV. First, I define two kernels, an averaging kernel, like a 7 by 7 matrix of 1 divided by 49. This acts as a blur kernel because it replaces each pixel with the average of its neighborhood. A sharpening kernel, which has a strong positive center value and negative values around it, is emphasizes edges and detail by increasing contrast near boundaries. Then I apply convolution in two different ways. With SciPy using SciPy signal convolve 2D, I convolve the grayscale image with the blue kernel, and the sharpen kernel using mode same, so the output size stays the same. With OpenCV using CV2 filter 2D, this function also performs convolution using a kernel, so it should produce similar results. For visualization, the program produces a composite figure with 5 images: the original grayscale image, blur with SciPy, sharpen with SciPy, blur with OpenCV, and sharpen with OpenCV. In the results, the blur outputs from SciPy and OpenCV are very similar, which confirms that both are performing the same low-pass operation. However, for sharpening, SciPy produces a clear sharpened image, while the OpenCV sharpened output appears almost completely white with only faint edges. This happens because the sharpening kernel can produce values above 255, and OpenCV clips or saturates those values when converting to an 8-bit output. So implementation details like data type and clipping strongly affect the final result.